Hello and welcome to today's webinar. I'm your host, Amelia Thompson, and today we are presenting ultra-compact and efficient switched capacitor power converters, presented by Würth Elektronik and Skycore Semiconductors. Presenting today's topic is Dennis Orlan Larsen, CTO with Skycore Semiconductors, and John Iscu Rodriguez, Product Manager for Capacitors and Resistors at Würth Elektronik. Today's webinar will run about an hour, maybe a little over, and if you have to step out, that's perfectly fine. Because you are registered, you will automatically receive the recorded presentation and a PDF of the deck within the following week. Simply be on the lookout for a follow-up email coming from webinarteam@we-online.com. That again is webinarteam@we-online.com. You can also reply directly back to that email if you have any follow-up questions or if we don't get to your question today. Because you are muted, you can chat away in our public chat, and there you can also ask your questions. Well, we really do enjoy seeing some repeated names here. It's nice to see you back again. I am going to hand it over to Dennis to begin today's webinar. Please enjoy ultra-compact and efficient switched capacitor power converters, presented by Würth Elektronik and Skycore Semiconductors.
All right, thank you so much, and thank everybody for being here today. I'm Dennis from Skycore, and today we'll talk about ultra-compact and efficient switched capacitor power converters. And to kick it off, I made a little quiz, like which of these products do you believe there might be a switched capacitor power converter inside of? And of course, it's a webinar online, so I cannot hear your answers, but it's also kind of a fake quiz that it's all of them. So you can actually find it in a lot of different places in the world today, which you might not expect, because most of the textbooks that you read on power electronics, either they don't mention switched capacitor power converters, or it's only like in the footnotes, essentially. So that's why we thought today we will shed a bit of light on switched capacitor power converters and give you some insights in where they can be used and how you model them, how you build them, and so on. And I believe afterwards, Jon will share some insights on the capacitors themselves. So first, a bit of background. I'm Dennis from Skycore. So we're a fabless semiconductor company, and we make power conversion integrated circuits that are optimized for switched capacitor power converters. And to get us started, we'll just look into why would you consider switched capacitor power conversion. So we first off define what is a power converter. It's probably familiar to most people in the audience, but just for the sake of this presentation, I will just briefly introduce it, that we have a power converter that takes some input voltage and a certain input power and converts it into the output, typically at a lower or higher voltage between input and output. Today we talk about DC-DC converters because that's what switched capacitor power conversion is specifically well suited for. And of course you also have efficiency measures, which is the ratio between the output and input power, which can also be expressed in terms of the loss, as you see down here. All right, so that's a very big picture. That's a power converter. And then why do we talk specifically about switched capacitor power converters today? And I believe that's because there's an increasing demand in a lot of applications in terms of efficiency, power density, and input voltage. And I'll get back to these in just a bit and show some examples where this is really shown to be the case. But we see a lot of applications where this is happening, and that really makes power engineers start to go down to first principles and start to look into, okay, how can you actually design the best power converter in terms of efficiency, power density, and also covering a high input to output voltage conversion ratio. And what we find is that switched capacitor power converters is really good at that in certain places. There's also some technology enablers which have made it possible to make very high power density switched capacitor power converters today, which was not necessarily available just a few years ago. So I will get into this in this presentation. We will look into some switch technology. We've seen, for example, gallium nitride transistors, which have entered the market, which has some parameters that are very well suited for switched capacitor power converters. Of course, capacitors that we will also later hear from Jon about their parameters and what is relevant for switch capacitor power converters. And then finally, topologies and integration, which I will also get into later. But first of all, some examples. So if you start at the very low end of the power range, you might have something like a hearing aid or a earbud, and you have around a 1 milliwatt power. And if you want to, for example, in a hearing aid, if you want to make it rechargeable, the voltage is at around 3.7 volt, where it in a non-rechargeable hearing aid is 1.2 volt. And if you look inside of it, to meet this voltage gap, you would put in a switch capacitor power converter to solve that issue. Also in smartphones, back in the day, you would charge your smartphone at around 5 volt with 1 amp, so around 5 watt, and it would take several hours to charge your phone. Today, you can charge your phone much faster. Some phones even go all the way up to 240 watt, which is an absolutely amazing charging speed. Most phones today are less than that, but still, to achieve that, you actually have a switch capacitor power converter right inside of the phone. So most of you will most likely have a switch capacitor power converter right next to you at this very moment. Very relevant now for when you hear about the AI revolution, that a GPU used to be just a few hundred watts, and today it's more than a kilowatt. And at the same time, we also see that the input voltage to something like this has went from 12 volt all the way up to 48 volt. So there's, again, a higher input voltage and also higher power in the same footprint. So you really see here that a lot is, changing in the application space, which will make you start to consider other solutions if what you have today is actually not able to meet these demands. And finally, we also see automotive, where we see a growing power demand for infotainment and ADAS, where back in the day it might be less than a kilowatt in the 12 volt supply. And today you even see some vehicles that have 48 volt supplies. It's not for the traction, but it's just for the main voltage for distribution to all the features inside of the car. And if you look inside of that, you might actually also find a switch capacitor power converter. So clearly, switch capacitor power converters are found in a lot of places today, and especially in places where you see a growing demand in terms of, first of all, power density. And just to give a bit of background and how that links to also the input voltage, if you look at the power density, let's say you have a phone. It's a fixed size. It hasn't changed. Maybe it's grown a little bit, but it's not 10 times larger than what it used to be. And if you then have a higher output power, and you have your input power into your converter is the output power divided by the efficiency. Well, if you increase the output power, you also increase the input power. And all this power has to be transferred to the power converter. So in the phone, it has to be transferred through the cable. In the GPU, it has to be transferred on the motherboard from the power supply. And what you find is that if you want to have 10 times, 15 times more power at the same voltage, so the voltage that distributes the energy into the power converter, well, you're going to have a problem because the higher input current will give you a lot more loss in your distribution, in your PCB traces and in your wires and so on. So you increase the input voltage. That is because when you increase the input voltage, you have a lower input current. And because the distribution loss is proportional to the current squared, well, then you get much lower distribution loss if you increase the voltage. So that's, for example, why we in the data center have seen you went from 12 volt to 48 volt, because that is a 4 times higher voltage. And because of the square, you will have a 16 times lower distribution loss here. And then finally, efficiency. So if you want to pack in more power in the same footprint, and the footprint is typically what sets your loss limit. So inside of a smartphone, you cannot really dissipate more than 1 watt. In a converter on a GPU, it might be 30 watts, but still there is a certain limit. And if you want to put out more power, given this limit, then the maximum output power you can deliver is proportional to the efficiency like this. So as you can see, when you increase the efficiency for a fixed loss budget, you can push out a lot more power through your power converter. And that's why you see in all of these applications that when you start to put a higher power density because you have higher power demands, you increase the input voltage because you want to reduce your distribution losses, then you also have to increase your efficiency at the same time because you want to push more power in the same space, so you need a higher efficiency. So these are really a lot of demands that you have to meet at the same time. And what a lot of power engineers has found is that you cannot, in all applications, meet these demands with a traditional buck converter, for example. And then you will start to look into other applications, other power converter topologies. And one of those might be a switch capacitor power converters. So to summarize the takeaways here, so we have higher power demands in a lot of applications. That's higher power density. And then because of the higher input current, you typically want to increase your input voltage to manage your distribution loss, at least what we see in a lot of applications today. And you also want a high efficiency because you typically have a fixed power loss budget inside of your application. And if you want to deliver more power inside of that same thermal budget, then you need high efficiency. So this is a bit of motivation. So first of all, switch cap is not something that's only found in papers in academia. It's actually found in a lot of applications today, and especially in applications where you want to push the limit. Because as we know, like power converters, traditional power converters, such as a buck converter, is used all over the place, and it meets the demands in a lot of applications. But it's really in these cutting edge applications where you see switch capacitor power conversion, it starts to pop up. And that's why we thought we would make this webinar to give you a bit of an insight and understanding of how they actually work. Okay, so let's look into the fundamentals of these switch capacitor power converters. I'll just briefly go through it. I will go in a bit of depth, but I'll not cover everything, of course, because this is it's just a single webinar. So we'll start out here, and if you observe these 4 different application examples that I showed, what we see is that in the small applications, such as a hearing aid or earbud, you might have a couple of milliwatts, while in a car, you might have kilowatts for the infotainment and so on. And what you observe here is that you need more capacitors if you want to process more power. And also you see here on the left, you most likely have integrated switches, also the case in the smartphone. But when you start to go up to higher power, you typically have discrete switches like this. So there's clearly some relationship between the power level and the number of capacitors and the size and the type of the switches. And how can that be? So let's just consider a simple example. This is a divide by 2 power converter, switch capacitor power converter. We have a flying capacitor that you, in one phase, you connect it to the input and the output, and the other phase, you put it in parallel with the output. So it looks like this. In one phase, you charge the capacitor, and in the other phase, you discharge the capacitor. So you switch the capacitor. That's where the name comes from, switch capacitor. Okay, let's then look closer into this power converter and see how it behaves when you start to simulate it. So here I picked some parameters for the different components. And if I simulate it and I don't have any load current, I see that it simply divides the input voltage by 2, which is what I would expect from a divide by 2 switch capacitor power converter. And that's really what switch capacitor power converters are really good at, dividing the input voltage by a fixed ratio. And that's what we see here. Okay, but what if we then start to put a load? So imagine here you have the load current, and if you start to put a load current on the system, then you see the output voltage start to drop. And this is really critical in switch capacitor power converters, and that's what most learning in learning how to work with switch capacitor power converters, it really focuses on this output drop, because that's what sets most of your losses in this type of converter. And if we don't want to try to model this, we can also look at the relationship between the output current and the input current. So again, imagine there's a load connected to this converter that draws a certain current in milliamps. Well, then we see it actually divides the current by 2. So it divides the input current is half of the output current. And as you can imagine, if you have half the output, the voltage at the output at 100 milliamps, let's say, and you have 24 volts out there, that's 2.4 watts. And that also has to be present at the input because you go, because you have double the input voltage and you have half the current. And that checks out on the conservation of energy. Okay, and what might we model this converter with? We can actually use a ideal transformer model. That's what you typically see if you find a textbook that actually covers switch capacitor power converters. Then you will see the ideal transformer model. And you should not think of this as an actual transformer with windings and so on. It's just a mathematical tool to model this relationship between input current, input voltage, and output voltage. And how it mathematically looks is like this. So your output voltage will be this ideal voltage conversion ratio times the input. So in this case, it's a half. So the voltage here is half the input. And if you don't draw any current through this output resistor, well, then you get the 24 volt in this case when you have 48 volt in the input. And the input current is, again, this ratio times the current that is flowing into the output. So that's the basic relationship. And what we saw here was that when we increase the load with a certain current, same step, you get also the same step in voltage. So that, I would say, alludes to that there must be a resistive nature in this power converter. And if we plot the output of having this model simulated next to this power converter, we actually see that it corresponds 1-to-1. So that's, of course, good to know that you can actually model most of the losses in a switch capacitor power converter by a simple model like this. That's, of course, a great starting point. The problem is then when you look into this, that the output resistance here, you have to model that somehow. You have to find an expression for that. And that's where it starts to deviate a lot from a typical buck converter, inductor-based converters, in that it actually depends a lot on your choice of components and your switching frequency, how you model this output resistance. So let's just explore the design space a little bit. So what I showed you before at 100 milliamp load was for switching a switch resistance of 100 milliohm and a flying capacitor of 1 microfarad. And you get a response like this. And then you might think, okay, I have a resistor here that I'm modeling the converter with, and I have a switch resistance as well. So what if I go ahead and halve my switch resistance, and try to guess at home or at work, wherever you're sitting, how do you believe this graph will change when you have the switch resistance? And let's see, it actually didn't change at all. So that's, of course, quite puzzling. And that's what makes it a bit hard, to get the intuition for switch cap converters to begin with. But I will show you in a bit how this works. And the next thing we could do is what if we then try to increase the flying capacitance? And what we see here is then we actually get a lower drop on the output. And as the way you should read this is that we are applying the load current at this point, and because you have a drop in the output voltage across that resistor, well, that's actually your main loss, is this I squared times the output resistance loss. And the loss is dissipated in the switches. So if you look at this is not the flying capacitor current, this is actually the switch current. So one of the switches will see currents like this, which are kind of these spikes. And if you want to calculate the RMS current of this, that can be a bit of a hassle. So what we typically do when the converter is operating like this is that we consider the flying capacitor voltage, where we see that is actually just complete steps from a certain voltage plus a delta V. And if we have something like this in a system, we can actually calculate the power loss by just considering the energy in the capacitor in the beginning of the phase. So this is phase 2, as we call it, where the cap is connected in parallel with the output. And the cap is therefore discharged from a starting voltage down to a ending voltage here. And I'll just go through the math rather quickly here, but you can always watch this later and delve into the details if you want. But the energy in a capacitor is fundamentally given by this expression. So it's the capacitance, half, and then the voltage squared. So we can look at the capacitor at the starting point and say, okay, how much energy do we have in the capacitor at this point? And we just said that we define the capacitor voltage as the output voltage, because we end up down here when we have discharged the capacitor all the way to the output voltage. So that's this point, plus some delta V. So that's what you see here in this expression. Okay, now we have it at the beginning. Then what about the end? Well, at the end, we have discharged it all the way to the output voltage. So then we have this expression. Then we can compute how much of this energy ended up in the output. And of course, in voltage is joule per coulomb. So if you know how many coulomb you put into the output and you know the voltage, well, then you also know the energy. And to get this expression into something that is related to the delta V, use the expression of a capacitor here. The delta V on a capacitor is the charge that you removed from it divided by the capacitance of the capacitor. And then you have finally this expression where we can see how much energy actually made it to the output. And if you subtract these two, you get how much did you actually lose in this exercise going from here to here. And you don't need to fully comprehend all of this now. What we really want to look into is this expression, that the loss is actually depending on the flying capacitance and the delta V. And if we take this one and we again use this expression for a capacitor, so the delta voltage is related to the charge on the capacitance, we can actually express this in terms of the charge. And how much charge did we move out of this capacitor in this operation? Well, it's actually, you find it by considering this steady state case, that you have some load current that you draw out of your converter. And then you have these two phases, phase 1, phase 2, phase 1, and so on. And what we're looking at right now is the phase 2, so where the cap is discharged. And in each of these phases, you draw 1 unit of charge out into the output. So we can say that if we know the load current and we know how much time this is, that's half the switching period, then you know how much charge you have at this point. So now we know what Q is. And therefore, we can derive the loss in terms of just the components you have in your circuit, the flying capacitor, the switching frequency, and the output current. And we go through to find the total loss. So this is just in one of the 2 phases. And the loss in the whole period is then 2 phases because it's a 2-phase converter. So you just multiply the whole thing by 2. And now we actually have an expression that is just the power loss of your converter. And finally, the last mapping is to say, okay, this power loss, it has an I out squared term. So this looks like something that is resistance times a current squared, which is the expression for power. And finally, we can get this output resistance. So this is what we aim to find. How much is this output resistance? And you can see in this specific case, it actually only depends on the flying capacitance and the switching frequency. And that explains why before, when I just divided the switch resistance by half and expected the converter to perform better, it actually didn't change anything. Because when we are in this operating mode, it's only the flying capacitance and the switching frequency that matters. And this is what we call the slow switching limit. Because you switch so slow that you get a full charge and discharge of the capacitor. And that's why, of course, capacitors are so important in a switch capacitor power converter. Okay, so now we have this expression. Then you might say, okay, let me just increase the flying capacitance into infinity because I want to have a very low output resistance. Because let's say I want to design a high power switch capacitor power converter. And my main loss is the output current squared times this output resistance. So of course I want this to be very low. So I just increase the flying cap and I expect it to drop by 1 over the capacitance. But what you will find is actually it's going to taper off. So at this point, when you start to add more cap, it actually doesn't change anything anymore. And again, we can look into the switch current. So this is the same kind of plot we showed before. We had the switch current and the flying capacitor voltage. And now we don't have these delta functions or spikes. We actually have something that starts to approach a square wave. And if you want to find the loss in the system, again, we look at the switches because a capacitor fundamentally doesn't have any loss. It's always the switches you have to consider. And if we have a square wave like this, or we can approximate it, because in the limit, when you make the flying cap infinite, you will get a square wave. We can do the same exercise and calculate the loss. And I've done that here. I will not go through the details here, but it's a similar expression. You have a square wave. And if you have a square wave with a 50% duty cycle, you have a certain RMS current. And from that, you can find the loss. And then we can express it in terms of this output resistance from our model. And the expression looks like this, 2 times the switch. So in this mode, when we have increased the flying capacitance so much that we're now entering this, what we call the fast switching limit, it's actually going to taper off at 2 times the switching resistance. And remember, I had 100 milliohm switch resistance, so this is going to taper off at 200 milliohm. Okay, so this is these two regions that you can operate a power converter, a switch capacitor power converter in. You have this fast switching limit and the slow switching limit. One is divided by the switching frequency, so you get this on a log-log plot. You get this slope, and the other one is a fixed limit that is 2 times the switching resistance, which is going to set your the minimum output resistance. And that's your maximum performance. So if you want to draw a lot of current out of your power converter, you want a really low output resistance. Because again, the intrinsic loss, as we call it, the main loss in a switch capacitor power converter is the output current squared times the output resistance. And this is the expression that we found here today. And this is a general expression, which is called charge flow vector derivation. And the cool thing about this is that all this derivation we just did, you don't need to do it ever again for more advanced power converters. You just need to find the charge flow vectors. And I'm not going to go through that today, but it can actually be done by inspection. And when you have that, you just put it into your expression here, and then you have your output resistance. And finally, people usually estimate the output resistance with an expression like this, because we have a defined output resistance at this end, so of this, I would say, asymptote, and at the asymptote down here. But in between, it's a little bit harder to model. And this is a good starting point. There's also more advanced ways you can model it, but this is a good starting point. Okay, so in summary, if you look at a switch capacitor power converter like this, what you have to think of is that you cannot just increase a given parameter, let's say the switch conductance. Like, you cannot just make your switches bigger and expect better performance. You actually have to also know what the flying capacitance and the switching frequency is before you can make design choices in your power converter. I think that's a big difference with the traditional buck converters, that this is really, how to say, these two different operating regions that you have to consider. Okay, so this was a bit of a deep dive into one single aspect of the switch capacitor power converters, just to give you an idea how you work with these power converters. And what we found was that the output resistance depends on the switch resistance and also on the flying capacitance. So it makes sense that you also look at the switches then. And specifically what I will look at here is the high power case, where you have discrete switches. And you typically have discrete switches because you want to distribute better the thermal dissipation in your power converter. So you cannot really have all the switches in a single chip if you want to push a kilowatt through your converter. And what are the critical performance metrics of the switches? Well, first of all, the switch resistance, because it's right there in our output resistance in the fast switching limit. So that's the main parameter that we look out for in a switch, for a switch capacitor power converter. We also have the gate charge, which is also very important. And also to some extent the output capacitance. But at Skycore, we have zero voltage switching technology, so we don't look too much at the output capacitance. But the gate charge is still relevant as well. And what we'll do next is to look at a lot of different discrete MOSFETs from several different vendors. And we're going to look at how MOSFETs and GaN FETs, they compare. And we're going to look at these two figure merits. So the first one is area times the on resistance. So if you can get a really low on resistance in a really low area, you have a really good switch. So you want this figure merit to be as low as possible. And here I plotted hundreds of switches for different maximum voltage ratings. And as you can see, for lower voltage ratings, you can get a better figure merit. That makes sense. If you need a 100-volt device, it's going to be bigger than a 25-volt device. But what happened then when GaN entered the game? And here you can see that for higher voltages, you get really, really good figure merit in terms of the RDS on. Not so much at the moment at the really low voltages, but they are actually starting to launch switches that are also going to be competitive down here as well. Of course, an aspect that you also have to consider is cost, which I've left out here, but that's something it will be part of the more detailed design of your converter, where cost, of course, also might make you want to pick MOSFETs for some of the switches, and maybe gallium nitride FETs for some of the higher voltage switches. At Skycore, our chips actually support both, so you can mix and match the switches as you want. The next figure merit is the gate charge. So because you have to charge the gates of all the switches, that's of course some loss that you're gonna have in your converter in a very similar way to in an inductor-based converter. And as we see here, generally, when you have a higher voltage switch, you also have more gate charge for a given RDS on. So you can just imagine this. If you have a fixed RDS on, how is the gate charge going to look? Well, it's going to increase for higher voltages. But again, we see here gallium nitride really makes a big impact on this figure merit, especially at the higher voltages. So if you want to make a switch capacitor converters for higher voltage, you should definitely consider gallium nitride switches. And for lower voltages, you will probably consider using MOSFETs or a mix of both. All right, that was switches. So in a switch cap converter, we of course both have switches, but also capacitors. I'll just very briefly mention the parameters that is important for us, and then I know Jon later will delve into a bit more details. But the most essential parameter for us is the capacitance, because it is right here in the slow switching limit output resistance expression. So we want as high capacitance in a smaller footprint as we can get. What we have to be very careful about is that when you start to apply a voltage across a capacitor, it will degrade the voltage depending on the type of capacitor that you have. So some high density capacitors, they will actually get a lower capacitance when you start to apply voltage to them. And that's very important because in a switch cap converter, like the one I showed you earlier, the capacitor would see 24 volt DC and only a small delta voltage on top of that. But of course, also voltage rating, the equivalent series resistance and equivalent series inductance is also important. But generally, mostly in very high power converters, you will start to consider these two parameters. And this is really one of the key insights on why switch cap converters can become very high power density. And that is if you consider how much energy can you store in a capacitor versus how much energy you can store in a inductor. So a capacitor, we saw the expression earlier. It's the voltage squared times C half. And in the inductor, you will have some kind of current. Here I put it at saturation current, squared times L half. And if you compare for a lot of different components, you get something that looks like this. And what you observe here, it's around 200 times higher energy density that you can get in your capacitor versus the inductor. I think Jon will also mention this, so I will not delve too much into the details here. But if you fundamentally consider a switch mode converter, so either a switch inductor or a switch capacitor, what you're essentially doing is you take small package of energy from the input and deliver it to the output. And this element that you put the energy into it, the higher the energy density you can have for this element, the smaller it can be for a given energy. And that's why it's attractive to use capacitors, because they inherently has a high energy density. Okay, so far we have seen a lot of switch capacitor converters in applications where you have requirements for high power density, high efficiency, and a high voltage input-output conversion ratio. But there's also a lot of challenges in making a switch capacitor converter, and that's also why you don't see it all over the place, because you do have more switches in your topologies, which would require more gate drivers, more level shifters, and so on. And that's constitutes these integration challenges that I will cover next. So I consider the topology and the microchip integration as part of the, you could say, the integration challenge and the integration solution. So the challenges overall is that your startup is a big problem in switch capacitor power converters. When you first turn on the converter, all the capacitors are at 0 volt and they would like to stay there. And when you then apply an input voltage, then you have to charge these capacitors in a gentle way so you don't damage the circuit. There's also more switches to control. There's more gate drivers, but also higher voltage floating level shifters. There's also control of all these switches and 0 voltage switching and so on. And that's what Skycore, where we come into the picture, that we actually integrate all these things into a single chip. So you can build your switch capacitor power converters without having to deal with all these integration challenges. This is just an example of a more advanced switch capacitor topology. As you can see, we have, again, switches, transistor switches, and flying capacitors. We just have a few more of them compared to what you saw earlier. But you can actually use the exact same framework that I showed you to analyze this converter as well. And we do that every day for all these advanced converters. So it's a very useful tool to have in your tool set. But as you can see, all these advanced switch capacitor topologies, here I just mentioned some names, they all have a lot of switches, typically more than a buck converter, which might have one switch in a diode or two switches. And all these switches in a switch capacitor power converter also need gate drivers and level shifters. And of course, we have to have capacitors, and sometimes you also have inductors if you want to do hybrid converters or if you want to do zero voltage switching, which I will not cover. I'll not cover hybrid converters in this presentation. But as you can see, all these discrete components, they will likely create hefty bill of materials and also a big solution in terms of size. And what we then bring to the table is integrating all of the needed components in terms of gate drivers, level shifters, and so on into a single chip. We also have built-in zero voltage switching technology, which allows you to do zero voltage switching with a very, very tiny inductor. And this is really the value proposition from our side. And we also have solutions where we don't use external switches. We actually have all the switches in the chip. And that's, of course, for the lower power applications, as you also saw earlier. I have just some scope plots just to show you some, how to say, real-world measurements of the startup of a power converter, a switch capacitor power converter. And what you want to see is that the output voltage is gently increasing. And that's also what we have some proprietary technology to enable that with just our single chip. Shutdown is also the same thing. We get a very gentle shutdown where we don't damage any components just by using our chip as the main part for integrating your power converter. I also have a few practical examples, some evaluation kits where you can see here a 50 watt, a 300 watt, and a 1000 watt evaluation kit. And here I've highlighted the solution size. So you have a chip, our chip, and a few capacitors that can make you a 50 watt converter. And if you start to use external transistors and a few more caps, you can make a 300 watt converter. And if you have more caps and more switches, or larger switches, you can make a 1000 watt, and we're also working on 1.2 kilowatts at the moment. This is just a demonstrator that we also have. So if you go to our website, you can see some material on our chips, and you can see here examples where our chip go into a board together with a lot of capacitors and a few discrete switches, and that implements a very high power density and high efficiency power converter. We have both gallium nitride and silicon versions of these demonstrators. So yeah, we make these reference designs for our customers to be able to test out our chips, which is our main product. That is the chip here that you can see. That's the Skycore chips. Another place you can also use switch capacitor conversion is active cell balancing. That's something you need in big battery packs. And here we also have an upcoming product for that uses some of the techniques that I taught you today, together with microchip integration, to basically increase the lifetime of big battery packs. And the main selling point of the switch cap solution is that it's a third of the price of what is out there today. Again, because you don't need a big transformer, you can actually do most of it with a few MLCC capacitors. Okay, that was actually all from my side, so I will just give a bit of a summary. So we looked into the different applications where we can see an increase in demands to the power converter in terms of power density, input voltage, and efficiency. And then we looked at different technology enablers, specifically switches. We got better switches. Both the MOSFET has become better over time, but also the gallium nitride switches. Capacitors have also become much better over time. And finally, topologies and integration is something we discussed, and how Skycore's chip can actually help you deal with some of these integration challenges. And finally, I just want to hand the mic over to Jon, and also say how we work with Würth Elektronik. So one way we work with them is, of course, the capacitors. We use different capacitors from different vendors, but some of them are from Würth. Also, for our proprietary zero voltage switching technology, we use a very tiny inductor This one is one of Würth's inductors that we use for enabling zero voltage switching in switch-cap converters, together with our chip. And finally, some of our lab test setups, we also use modules from Würth to have household voltage supplies available. Okay, that was all from my side. So I hope this gave you a bit of, a bit of a peek into switch capacitor power converters. It also showed you, hopefully, that it's something you should pay attention to because it's on the rise in a lot of applications. And finally, you can feel free to reach out to us if you have any questions. Thank you very much.
So I think, I think you can hear me now. And hopefully you can see my screen. Thank you, Dennis, for the presentation. It's really interesting. And thank you for giving way. So my name is John Isco Rodriguez. I have been working for almost 7 years in the product management of capacitors and resistors inside Würth Elektronik ISOs. And my presentation is going to be very short because this is already a long presentation. And I want to answer the question, what capacitors are suitable for the applications we just discussed in switch capacitor converters. So as an introduction, I want to show you this graph. It's similar to what Dennis was showing, which this one was created by the researchers from the University of California, Berkeley. And this is the result of a survey of over 500,000 capacitors and inductors from several vendors. And each represent a point in a graph. And I have taken the liberty to copy the formulas from Dennis' presentation about the energy to be able to be stored in each component. And in orange, you can see, 1 second. In orange, you can see the inductors, which are distributed in the horizontal plane by their current rating, and the blue points are the capacitors, which are distributed by the rated voltage. And interestingly, the vertical axis is the volumetric energy density, which is in the same scale for both capacitors and inductors, in logarithmic scale, of course. And as you can see, here, the possible energy to be stored, to be used in the conversion per cubic millimeter or whatever, per volume, can be up to 1,000 times higher in capacitors. So this is an indication, as Dennis said, of the possibilities of very compact and light converters. So let's look at the different capacitor technologies. So I'm not going to go into detail about what it means in each capacitor type, but if you are interested in this presentation, we can give you a link to all the webinars. And in theory, any capacitor can serve as flying capacitors or switch capacitors in this kind of converters. This is going to be a long slide, so bear with me. Looking at what Dennis said in the presentation by Skycore, these are the requirements that we have considered the most important for capacitors, and we require high capacitance values, which is important, and they have to be in very small packages to keep the design small and compact. So there is a considerable ripple current due to the charging and discharging the flying capacitors. I mean, I don't even know if ripple current is sometimes not even the right word, but yeah, charging and discharging current. And we require low ESR to keep the losses low, and get efficient converter. And low ESR means normally in the specification high current. we need a small package, as we said before, and also because to keep the ESL slow, the parasitic inductance. And this is important for high frequency switching, which is how we also achieve these high density converters. So yeah, of course, we have the ceramic capacitors, which of course you have seen them in every image of the converter, and we divide the ceramic capacitors in class 1 and class 2. Of course, I will only speak about the MSCC, so the multi-layer chip, which is what is commonly used and the more common. And I will explain later what are the details about using class 1 and class 2. Then we have the aluminum electrolytic and aluminum polymer type of capacitors, also hybrid. So these caps have also very high capacitance values, but we are very limited. In electrolytic, we are limited by high ESR, so we can only have a very small current and until the capacitor gets really hot, and we are limited by lifetime due to high temperature operation. And the polymer types, in theory, it's an improvement on current and low ESR, but we may run into limitations due to their size or the low profile. In many of the applications mentioned by Skycore, there is a wish or a requirement of I don't know, a maximum height of 3 or 4 millimeters, which is not achievable with this kind of packaging. There's a special type, which is the H-chip polymer types, which has another construction. It's like an interleaved sandwich of polymer layers, sometimes called multi-layer polymer chip or aluminum multi-layer chips. So these are in the same package as the tantalum chips, and they offer really, really high capacitance and really low ESR. So are very interesting also for this kind of applications, but we are limited, at least in our case, to working with low voltages. And there are other limitations around current at at a lower frequency operation that can happen. Finally, we have the film capacitors, which most commonly use metallized polypropylene, like this kind of boxed film capacitors, which in theory, yes, they are big and bulky for this kind of applications to achieve high capacitance, but in specific cases of high voltage application, this could be interesting for other applications different from the from the Skycore chips. So in the case of the applications described in this webinar, these two capacitor types are the most adequate, especially talking about the flying capacitor, of course. And the reason is, we say it many times, the high capacitance density. And another advantage is the low profile. So I'm going to focus on the most commonly used multi-layer ceramic capacitors. And as I said, there's class 2 and class 1. In the class 1, which sometimes the most commonly used type, sometimes is written NP0 or COG, which is or C0G, is just two different naming schemes for one specific requirement, which is extreme stability of capacitance. So we have components that are relatively low capacitance, but for this we have very low loss, low ESR, and very stable capacitance values. So there is no capacitance drift, and this makes them very suitable for applications where the capacitance has to be exact. So, for example, in resonant converters or in oscillators, etc. But of course, due to the low capacitance, these are not very suitable for converters such as switch capacitor converters. On the other hand, class 2 capacitors, we have really high capacitance possible. And everywhere where we have a bulk capacitance requirement and a small size, you will find these kind of chips, ceramic capacitors everywhere on the board. So sometimes you have seen names like X7R, XXS, or X5R, and more, which is just an indication of their temperature range and the drift that is possible inside of the temperature range. So this drift is limited by this kind of types, but um, these ceramic materials, which are used as the dielectric here, have really high permittivity, but they have a property that is called ferroelectricity, which is just a naming borrowed from ferromagnetic materials, which just means that the capacitance values are not stable over temperature, operating voltage, frequency, and there is aging, there is hysteresis during charging and discharging. So there are all of these effects which make the permittivity very variable. So this is what this is the let's say the drawback of using these high density materials. So as you can see, we are able to create to get hundreds of microfarad in one package, which is about 1,000 times higher capacitance density that type class 1. But we have a bunch of problems with this. Another undesired property is what we call piezoelectricity, which is just that they may be with electrical field variation. There may be there is a mechanical constraining or mechanical stress in the electric field, and we can have cases of vibration and other um, undesired interference. So this is what we have to take into account when you use class 2 capacitors. And to show you again the density or the distribution of our portfolio, I sorted by capacitance and by rated voltage. And as you can see, all the high capacitance components, also for high voltage, are class 2, which are the ones in red. And the blue ones are interested in the very low capacitance values, and in the middle are class 1. And there is also overlapping, and this is because sometimes we have a very small class 2 capacitor with the same voltage and capacitance properties as a very big class 1 capacitor. So sometimes regarding the size, there is let's say another dimension to be taken into account when seeing the portfolio or the distribution of values which are available. So we are talking all the time about size, and we have to understand that we are speaking of very different size of components. This is the smallest capacitor that we have in our portfolio, which is 0201, which is 1 millimeter wide, long, and half millimeter wide. And this is a picture of the biggest ones that we have in our catalog, which is 2220 size code, 6 millimeter long, 5 millimeter wide. For comparison, and this is as a reference, €1 coin. So we are talking of really small components. And as you can see, there is a lot in between these sizes, and there is a lot of room for different distribution of parallel capacitors of different sizes and different geometries. So we could fit like hundreds of the smallest 0201 parts inside the footprint of this €1 coin. On the other hand, we could fit maybe 8 of these ones and maybe get better properties or worse. So this is something that can be considered in any case, in every case. So speaking about size, again, I hope you already know the DC bias effect, this I mentioned before. So for class 2 capacitors, increasing the applied voltage, the capacitance sometimes can drop significantly, or sometimes it drops more, and sometimes it drops a lot. So in this graph, for a comparison, I have the plots of capacitance versus DC voltage of 4 MSCCs, which are 1 microfarad and 50 volt rated voltage. And as you can see, the capacitance drops much more for the smaller components, which are these ones. This is I 1812. No, sorry. Yeah, this is a 0805 size, and the one in blue is 1812, so the biggest size in the comparison. And this is because there is um, smaller dielectric thickness, or less thickness of dielectric between electrodes in the smaller size. So the electric field is distributed strongly. Is a more strong electric field in this very small or very thin dielectric layer, and then we can only we can only show you that the miniaturization of components has this kind of drawbacks. So as you may know, if you work with ceramic capacitors, this is not part of the specification. So we are explicitly specifying capacitance at 0 volt DC in the datasheet, but we have measured this kind of curves for every single component in the portfolio, and this is important that you understand that we save these measurements for you in RedExpert, which is our online platform. Now I'm going to explain a little bit more about RedExpert, which is our online tool, which is mostly used for component selection. And yeah, you can find it in our website with this address, or clicking in the website, and also in the individual components in the online catalog. And it's completely free to use, although there are some advantages when you sign on. So we have powerful design tools like the inductor selector, with loss calculations for different converter topologies, and also there is a EMC filter designer, for example. But yeah, in the capacitor selection modules, which is what I work with, we take a lot of effort to measure every single part and give you more information than is strictly datasheet specification. So I can show you this example from the MSCC module. Let's suppose we want to filter ceramic capacitors for 1 microfarad and 50 volt, so the same example as before. And we can click the filter button of each column here, where I have put these arrows. And if you register, you can also use this. Sorry. In these buttons, I can select some components, and for these components, I will get the measurements, the graphs of the measurements. And if you register, as I said, you will get some other functionality, which is, for example, these sliders that I have set here and here. And I have moved the sliders, for example, to 100 kilohertz, and I get the values from impedance and ESR in the main table, like here. I can also move the DC bias curve. Yeah. And as you can see, for example, 24 volt, I get the values directly in the table from this curve. And you can see more or less the same results which I showed you before. Of course, at 24 volt, you may have less, less difference between the different sizes than at the rated voltage. And of course, this is another room for the designer to work around limitation of the components. So as expected, the orange part, which is the biggest one, will be kind of fine at 24 volt. We have a measurement of about 900 nanofarad, which is totally acceptable. But yeah, the blue one, the smallest part, will have, even at 24 volt, already a significant loss of 30% capacitance. Yeah, finally, just a reminder. This is the commitment to provide accurate characterization of all the parts. So we measure all capacitors for impedance, and of course, in the case of MCC, we measure the DC bias and other measurements. So this information is going directly to the expert with no processing. This is raw measurement values for reference. They only represent one instance of one lot of many average of many measurements. And what we also do is we calculate we calculate a fitting of the equivalent circuit. So we calculate how to describe these measurements with a simple equivalent circuit, and we have a mathematical model which we have created to model the behavior of DC bias. And there's an EPNOTE which I showed you before in the previous slide, which also contains the calculations of how we come up with this formula. And what we do with these simplified models is that we provide you a simulation library and simulation models that you can use in SPICE, for example. So in this case, for example, we offer the full library in LT-SPICE, but in any SPICE program, you can use the same formulas and the same model calculation. And then the DC bias, it will be also considered in your design. So it will it will be included in the output of your simulation. So also from my side, thanks for coming to see us online. And I think we will answer some questions now, probably first with Dennis. And yeah, maybe.
Yeah, sure.
Yes, thank you guys very much for presenting today. We do have a few questions that have been coming on in, and we are going to start now. As a reminder, in the event that your question does not get answered, you can always reply back to our follow-up email. That is webinarteam@we-online.com. Our first question that came on in was regarding regulation. Can you regulate the output of a switched capacitor converter?
Yeah, so as you saw in the model, on the output of the converter, you do have the resistor, and you can actually regulate that if you want. So you can change the switching frequency. That's the most typical way you can do it. But it's, of course, a lossy regulation. So typically, you don't want to do that in a high-power design. So typically, what you do instead is that you have a downstream or upstream regulation, and then the switch cap converter is just an intermediate step down. So, for example, in the phone that I showed you, these fast-charging phones, they actually have a fixed ratio converter inside of them, and then the regulation happens inside of the charger that you plug into the wall. So that's a way that you can also see how designers are restructuring the power system to meet these demands. So here you cannot dissipate that much power in the phone. So pick a switch cap converter, fixed ratio, very high performance, and then you do the regulation in the power brick that you put into the wall. So yeah, in general, you can regulate, but only at low power. And at high power, you typically do it on a system level, you could say. You put the regulation somewhere, but typically not directly in the switch cap converter.
Excellent. Thank you for explaining that. Our next question here. Do you want to operate the converter in the SSL or FSL region?
Yeah, so that also relates to this output resistance that I showed, and specifically FSL was where it's completely limited by the switch resistance, and SSL is where it's the product of the flying cap capacitance and the switching frequency, so 1 divided by that product. And typically you design your how to say converter such that you're kind of in the sweet spot between the two, because you want the switches to be as high resistance as possible, because the high resistance is a cheaper transistor, and then you pick the capacitor to kind of match approximately the fast switching limit resistance, such that the slow switching limit and the fast switching limit resistance is approximately the same. Typically what you do. In a low power design, you might want to have a bit fewer capacitors because they take up a lot of space. And if you can integrate all the switches, they don't take up as much space. Whereas in a high power design, you might want to go further into the fast switching limit, where you're more limited by the switch resistance. So that's the big picture, how I would say the trade-off is.
Thank you very much. This one looks like it came in for John. What is the impact of DC bias on the performance of the switched capacitor converter?
Okay, yeah, thank you. Yes, it's a good question. I think the impact can be quite big. So as we saw in the measurements, in the end, there is a big uncertainty of what is going to be the final capacitance value on your application, because also, as I said, it will also vary with temperature and frequency, but especially, as I said, with DC voltage. And in most of the cases, there will be an area of uncertainty which can be estimated, at least in a worst and best case, more or less. And this has to be taken into account during the design of the switch capacitor converter. And as far as I understand, there will be certain room or space to tolerance for it to work inside of these certain capacitance values. So of course there is some simulation and some testing to do, and yeah, it shouldn't be that big in short. But yeah, maybe Dennis can complete the question from this.
Yeah, thanks, Jon. I think you got it. It does change, and then you take that into account when you design the converter. Specifically, if you have to design for a given input voltage range, then you have to bear in mind that when the voltage of the input is low, then you typically have more capacitance than when the input voltage is high, because as you saw on the Jon's curve, the capacitance drops when you start to have a higher DC bias. So it's definitely something you have to take into account in your design. So to make sure that the converter meets all specifications and all input parameters, you could say.
Thank you both for explaining that. Now, we are talking at the beginning of Dennis's presentation, you had that trick question of where is this technology used, but where do you see switch capacitor converters being used more in the future?
Yeah, so for sure in all high power, high density applications. So as I also mentioned in the presentation, there's a lot of applications where you just use what we have already today. But you also see in the world that a lot of applications start to demand much more power. I think one good example is the data centers, where due to the AI boom, we see that a typical data center rack, so the big racks you have in the data center where you have all the servers in, they used to be around 10 kilowatt of power, and now they're talking about 1 megawatt, so that's 100x. So I believe that's another place where you will probably see more and more switch capacitor power converters. And in general, wherever you look, where you see applications that have higher power demands, I think they will start to pop up.
Absolutely. We do have time for just a couple more questions. Again, if any questions come in, we will reach out directly after the webinar. But you can always reply back, webinarteam@we-online.com. What are the most common, or what are the most important losses in switched cap converters?
So the most important is what I showed, this loss in this equivalent output resistance. And that's also why I decided to spend most of the talk on that part, on the fundamental of this output resistance, because that's really what you have to model. And that is what depends on the capacitors and on the transistors that you use. On top of that, you also have the gate charging laws, you have switching laws, and so on. But they're more or less similar to how you would derive them for a typical inductor converter. So I think a lot of power converter designers, they would know how to do that. But this output resistant loss is really the big one. And that's what depends on both the switches and also really good modeling of the capacitors, which I can see Jon presented, how all these parameters is something we would fit into a simulation model before we do any PCB prototyping.
Absolutely. And we're just going to wrap it up with this final question. It was covered a little bit during the presentation, but what are some common pitfalls when prototyping the switched cap converters?
Yeah, I think the biggest one is the starting it up without blowing it up. That's really a very fundamental thing. But the thing is, when you have a capacitor at a 0 volt, the fundamental physics of capacitance is that it wants to keep the voltage where it was. And when you then suddenly apply a high voltage on a converter, then you will have potentially very high voltage drops across your switch, and then you might break the switches. So managing the startup is a big one. And then otherwise, there's all the parasitics. I think for low power design, it's mostly capacitive parasitics. So that would be coupling on the PCB and so on. Whereas for high power design, it's more the ESR, the resistance in the PCB, and also the capacitors, and also the inductance in the PCB and the capacitors. So that's again where you would look into the Red Expert tool, I believe, and look into these parameters where if you want to make a very high power switch cap converter, because you have to monitor these parasitics and have a good model of them before you go to the lab. And then once you go to the lab and prototype, you have to see if it fits with what you expected.
All right. Thank you both very much for presenting, Dennis and Jon. We greatly appreciate having you on our webinar today. Thank you so much.
Thank you. It was a pleasure.
Thank you, and have a nice day.
And thank you to everyone who joined us for our presentation. Now, as a reminder, in the event that we didn't get to your question or you think of one later, you can always reply back to our follow-up email. And because you registered for today's webinar, you will automatically receive the recorded presentation and a PDF of the deck when it becomes available. It should be to your email within the next week. So be on the lookout. Again, webinar team at we-online.com. And you can also reply directly back to that email. At the bottom of the email, be on the lookout for a link to register for our next webinar. It is coming up on July 29th. It's impacts of the degradation of molded power inductors in a DC to DC converter. So you can also catch up on your studies by listening to the Würth Elektronik What's Up podcast. If you are on the go, then the What's Up podcast is available as audio and video on certain streaming platforms. But you can find the podcast on all streaming platforms, including Spotify, Pandora, SiriusXM, iTunes, YouTube, and so much more. Just catch up on all the episodes at www.we-online.com/podcast. Thank you, everybody, for being with us today, and I hope to see you soon.
Thank you so much. Bye-bye.
Bye-bye. Bye-bye.